Okay, so today we will discuss about energy in simple harmonic motion. Okay, yesterday we were discussing about springs in parallel, springs in series, and we have just started discussing about the time period and frequency of a spring mass system. We have derived the velocity acceleration of a simple harmonic motion. So with that background, we will discuss about the energy in simple harmonic motion. Okay. So we were telling about the velocity, and we were discussing that velocity is maximum at the center in a simple harmonic motion at the mean position, about which the point oscillates. The velocity is maximum at that location, and then it is zero at the extreme position. Okay. So we know the expression for velocity in is r mv square, right? We know expression for velocity, expression for kinetic energy is r mv square. Okay. Then what is v? Like we know x is equal to a cos omega t plus I. Then we have derived that velocity is equal to dx by dt, which is nothing but we have derived it as a into omega. Okay, a into omega, then sine omega t plus phi. Sine omega t plus phi, and there is a minus sign here. Derivative of cos omega t is minus omega sine omega t. Okay, so that is the expression we have got. Then if we replace that velocity here, this becomes half m, then that is v square. When this negative term is squared, it will become positive. So it will become half m a square omega square, then sine square omega t plus phi. So this is the expression for kinetic energy. Okay, and this is also a sinusoidal function, and kinetic energy is also a sinusoidal function. So this kinetic energy will also vary from 0 to 1, because sine varies from 0 to 1. Okay. Similarly, sine square omega t also will vary from 0 to 1. So it is maximum, like during the course of the simple harmonic motion, it will vary from 0 to 1. Okay. Now, it's a periodic motion being 0 when the displacement is maximum when the particle is at mean position. Okay. So when the I have a spring mass system, and let us say I have a simple pendulum. So my pendulum is going like this, is going like this, so like this. So when it is like this, so we have told that at this location velocity is maximum, at this location velocity is 0. So that is about kinetic energy. Okay, and similarly there is potential energy. Okay, so potential energy, like the so let us say you have a spring and you have a mass. The, this stiffness of this spring is A and the mass is N. Okay. So when you are disturbing this spring, it is moving from the mean position, going back from the mean position. Okay, and it is moving toward. So this is kinetic energy. Then potential energy. Potential energy is normally here it's nothing but the work done. Work done will get stored as potential energy. Like you might have seen, like suppose I am I am taking a mass of weight m to height h. So mass m I am taking from the ground to height h. So what is the force acting on it? Mg is the force due to gravity working on it. And I have taken it against the gravitational force. So mg into h is the potential energy at height h. Okay. So in this case, this there is a restoring force acting on it. On this mass, when the mass is going like this, there is a restoring force of minus kx acting on this mass. That force into the displacement. Okay. So ideally it should be kx into x, but because it is varying from minimum to maximum, it is not like kx into x. It is half k into kx into x. Sometimes, so that is the potential energy of this spring mass system. So it is half kx square, half kx square. So that is the potential energy. Okay. So your kinetic energy expression is this, potential energy expression is this, and you know x is equal to a cos omega t plus I, right? So in this case, you replace this x by a cos omega t plus phi, a, okay, then a square cos square omega t plus phi. Yes. So this is the expression for potential energy. This is the expression for kinetic energy. Okay. So the total energy at any, so you can see here in this pendulum, because here the velocity is zero, here the velocity is maximum, here again the velocity is zero. Okay. So at this location, because velocity is zero, so total energy is potential energy only. So at the extreme position, the total energy is potential energy. Whereas the middle total energy is kinetic energy. In between, in the intermediate location, it is a sum of kinetic energy plus potential energy. Okay. So what is that expression? Like that expression is like, okay. So the total energy we write as E. U is your potential energy. K is your kinetic energy. Okay. So U half A square cos square omega t plus. Okay. So that is your potential energy. Okay. Plus another is we have written half. So here in place of m a square, okay. So in place of m omega square, actually, this m omega square. Okay. So it will, what is m omega square? So m omega square is equal to k actually. How? Because omega is equal to k by m. Okay. Okay. So we have studied like omega is equal to square root of k by m. That we have studied. Right? We have studied omega is square root of k by m. We have already discussed. Yes. So omega is equal to k by m. That means omega square is equal to k by m. Omega is equal to square root of k by m. So omega square is equal to k by m. That means m into omega square is equal to k. So instead of this, we can write it as half k m omega square in place of k m omega square. You can write it as k. Okay, because k is coming out to be m omega square, right? So instead of m omega square, you write it as k a square. Okay, then sine square omega t plus r. Okay, so you have written both in terms of this thing. So this in terms of amplitude, this in terms of amplitude. So 1/2 k omega square sine square omega t plus 5 plus half k a square cos square omega t plus 5. So one is sine, one is cos. So this is kinetic energy, whereas this is potential energy. Okay. So your this is your potential energy. You have written as this. Then your kinetic energy will be write as half k square sine square omega t plus 5. Right? So this is your total energy. Okay. So uh, at any location, uh, um, at the total energy will remain constant. Okay. So when the kinetic energy will be maximum, the kinetic energy will be maximum here at the center. The kinetic energy is maximum. When the kinetic energy is maximum, this potential energy becomes zero. Yes. And when potential energy is maximum, it is maximum here. Okay, it will be maximum at these two extreme positions. Potential energy is maximum because it is climbing some distance. Okay, so if you take the common, okay, if you take common a square, then it will and inside it will become something sine square plus sine square. Let us say this whole thing is let us say some sine square alpha plus cos square alpha or whatever this omega t plus 5. So this becomes one. The total energy of a spring mass system is half k square. Half k square. So if you know the amplitude, you get to know what is your total energy in this motion. Okay. So if you draw a plot of total energy, so this is your total energy. If you draw a plot, okay. So in the y-axis you have energy. In the x-axis you have time. Okay, with respect to time. Energy versus time. Okay. So you will have, like say, you will have a on and then like this. Okay, and then you will have a curve. So you will have a curve like this. So you know kinetic energy. This is sine. It is a function of sine. So at 0, t is equal to 0. So if the phase angle is 0, that means this which is starting from 0, that is kinetic energy. So this black curve is kinetic energy, whereas this blue curve is potential energy. This blue curve is potential energy. or this potential energy we uh, yeah. So this uh, so this is kinetic energy in this, and this is potential energy. So total energy at any location is kinetic plus potential. Okay. Total energy. So here you can see this is max and this is zero. This is max here. This is zero. So this is max. This is zero. So here it is max. It is zero. Okay. Max, max zero, max zero, like that. So total energy. Okay. So this is the time versus energy graph. Okay, and you can find out that at any location the total energy will become half Ka square. At any location, the total energy will become this expression. So let us say let us say this black is kinetic energy. So this kinetic energy and this blue is potential energy. Okay, so this is black is kinetic and blue is potential energy. So, mm, mm, so at this location, you can see the kinetic energy is maximum, the potential energy is zero, and the total energy, the addition of both, it will be half Ka square. Okay, at any location. Okay. So that is, you just remember what is the total energy, half Ka square. So if you know the amplitude of the motion, then the total energy is half Ka square. And remember that the maximum velocity is at the center. Okay. At the mean position, the velocity is maximum. At the extreme position, velocity is equal to zero. Kinetic energy is equal to zero. Okay. So we'll do a numerical. You take a picture of this. So we'll do a numerical on this energy in simple harmonic motion. We'll solve a numerical which will give us better. So both kinetic energy, potential in SHM are seen to be always positive. So energy is always positive. So kinetic energy can be, of course, can will never be negative. Okay, since it is proportional to square of the energy in potential energy, both kinetic energy and potential energy peak twice during each period of the session. Okay. 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 So let us do a numerical. Whether these are the driving principle. We can solve n number of numerical based on these equations. So one can ask what is the energy at the extreme position, what is the energy at the mean position, what is the energy at somewhere in between the mean and extreme position. So there can be so many questions. Okay. So can we read out what is written?
A block
Slowly. Okay.
a block
Hmm.
whose mass is
I am writing mass. Mass is
1 kg
1 kg. Okay.
is fastened to a spring.
Is fastened to a spring. So this is a block, and this is fastened to a spring. its mass is 1 kg. Okay, then
The spring has a spring constant of 50 Newton per meter.
how much? 50.
Hmm.
Hmm.
The block is
Hmm.
pushed to a distance x is equal to 10 centimeter from
Okay,
its
1 second. 10 centimeter. Okay.
from its equilibrium position
Okay.
at x is equal to 0 on a frictionless surface
Okay.
from rest at t is equal to 0.
Okay.
Calculate the kinetic potential and total energy
Hmm.
of block
Hmm.
when it is 5 centimeter away from the mean position.
Okay. 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 So they're telling the mass of this in this mass attached to this spring is 1 kg. The stiffness is equal to 50 Newton per meter. The spring always has a stiffness. So we have discussed that stiffness is nothing but force per unit displacement. So that value is 50 Newton per meter. Okay. And it is written the block is pulled to a distance 10 centimeter. So let us say the block was here, this is the main position. It is pulled to 10 centimeter, to a distance of 10 centimeter from its equilibrium position at x equal to 0 in frictional surface. From rest at t is equal to 0. Calculate the kinetic energy and total energy of the block when it is 5 cm away from the mean position. So at this location, so this is the extreme position, 10 centimeter. So it will go back. It will go back and it will go to this 10 and this 10. It will go like this. Okay. So its amplitude is 10. So at 5 cm location, what is the kinetic energy, potential energy, and total energy? That is the question. Okay. So uh, if you equate it to a simple pendulum case, like say this and like this, so it is like say it will go from here to here. So we are asking in the middle how much is the kinetic energy, potential energy, and distance. Okay. So we know like in the previous derivation we have derived actually we have equated two things and we have derived one expression like hmm. So we have told F is equal to ma. Okay, F is equal to ma and ma is equal to like acceleration is equal to omega square x that we have studied. Okay, omega square velocity is omega x. This is omega square x. So m omega square x. That is one expression. Okay, and then f is equal to also kx. Right, f is equal to kx. Okay. So from this you derive everything. Okay. So when you this is minus kx. Okay. So this is minus m omega square. Okay. So when you compare everything, it becomes k is equal to m omega square. Okay. Here k becomes equal to m omega square. So omega is becoming k by m. K by m. So with this understanding of angular frequency or angular velocity, we can find out what is our omega here. Okay. So omega is equal to 50 divided by, let us say it is 1 kg. Okay. Everything is in SI unit here. Force is in meter. This is okay. This is that will look into it. So K by M. Okay. So K is 50. Mass is 1. Right.
Yeah.
Right. So it becomes angular velocity is equal to 50 by 1 whatever. That is the omega value. Okay. Okay. So we know like we want to find out the energy. So for that we know your velocity is equal to a cos omega t plus phi. A cos omega t plus phi. So in this case, what is the amplitude? It is 10 centimeter. Amplitude is equal to 10 centimeter. Why? Because it will go till this point. It will go 10 here and it will go up also 10. It will go up also 10. Go down also 10. So that's the amplitude. The amplitude is equal to 10 centimeter. Okay. Which is nothing but 0.1. 10 centimeter is equal to uh, 0.1 meter. Right?
Yes.
10 centimeter is 0.1 meter. So, so if you replace your, you will find your omega value. If you replace k 50 and 1 and all, you will find it is 7.07 radian per second. See, remember the value of angular velocity unit is radian per second. Don't forget that. So we got this to be 7.07, and then we'll get therefore when the particle is 5 cm away from it, we have uh, xt. So when the particle is 5 cm away, also that means your displacement is equal to 0.5 meter, right? 5 cm. So 5 cm is nothing but 5 by 100, 0.05 meter, right? Right?
Yes.
So your 0.05 is equal to zero point 0.1, okay, into 0.05 is equal to 0.1 into cos omega t. So omega is 7.07 into t. Okay. So you assume the phase angle to be 0. It starts from phase angle in this case is 0. So your 0.05 is equal to this much. If that is the case, then so so 0.5. Okay. Okay. So this becomes cos 7.07 t is equal to 0.05. If you divide by 0.1, it will become zero point 0.5. Okay.
Yes.
So cos 7.07 t is equal to 0.5. Okay. Uh, 0.5, 0.5 means it is nothing but half, right? So it is cos 30, cos 30, cos 60 is half, right? So cos 60 is half, then sine 7.07 t will be root 3 by 2. Because cos 30, cos 60 is half, sine 60 is equal to root 3 by 2. So this equation, this is one equation. Okay. Okay. Then sine root 3 by 2. So these equations we know. Uh, so you don't worry about the time now, but at least you know, okay, at this displacement these are the two expression. At displacement of 5 cm, these are the two equations. Okay, so we know the velocity of the block at 5 this thing and the kinetic energy and potential energy, all these things we can write. So we know velocity of the block at 5 seconds. So we know what is velocity. So we know velocity is equal to derivative of d by dt a cos omega t. Okay. So if h angle is 0, it will become omega a sin omega t. This is the velocity. Okay. The velocity, the velocity. Okay. So the velocity of the block at x is equal to 5 centimeter. So, okay. Second point, velocity of the block. So we know your omega is 7.07, right?
Yes.
Okay. And you know your amplitude is nothing but 0.1. Okay. Then your omega a, and then sin omega t. Okay. So your sin omega, 7.07 into t. Okay. So sin 7.07 t is nothing but your root 3 by 2. Okay. So 7.07 into 0.1 into root 3 by 2. Okay. So this is your velocity. Okay. So the velocity, you will find it to be, if you multiply, you will find it to be 0.61 meter per second. Okay. Right. So if you replace all these values, you will get it.
Simplify.
If you simplify it, you will get that. So that is the velocity. Oh, so what is the kinetic energy? So kinetic energy is equal to half m v square. So to find energy in joule, your mass should be in kg, your velocity should be in meter per second. So after replacing everything, you will find it to be 0.19 joule. Right? So that is your kinetic energy. Okay. That is your kinetic energy. Similarly, the potential energy is uh, the potential energy is equal to the potential of k x square. That is the potential energy we have already studied, half k square. So we know the value of k already. So k is given 50, and x also we know it is 0.05, like 5 centimeter, 0.05. So if you replace, like p is equal to half into your k value is 50 Newton per Newton, then your x value is nothing but 0.05. So this square. Okay. So this is your potential energy, and if you replace everything, you will find this to be 0.25 joule. 0.25. So at this location, or at this location, here at 5 centimeter displacement, your kinetic energy is 0.19 joule, whereas your potential energy is equal to 0.06 one 0.0625. So 0.0625. 0.0625 joule. Okay. So The total energy is equal to 0.19 plus 0.0. So total energy is equal to 0.19 plus 0.06 is equal to 0.25.
Total energy.
This is the total energy. Okay. So, so you can see like how the energy varies and like at any location how the energy varies. Okay. So this is an example. You can extrapolate to it to in number of examples. So this is about the energy in simple harmonic motion. Then next we will do some oscillation of string problem and derivation of time period. Also simple pendulum derivation of time period and frequency for simple pendulum. So that will with that we will component of pre-oscillations. Then we will get into damped oscillations considering the friction, presence of air resistance and friction. Okay. So we'll solve some numericals on time period of spring mass system, time period of simple pendulum in the next class. Okay. So you can take a picture of it. Okay. Thank you.